Swayam Prabha. Digital India. Educated India.
So we have 4 plus 1 more lectures to go, and after that, what? 4 plus 1. The 5th one, I'll figure if I need it. If I need it, then I'll give that lecture. Okay. Great day today? Yeah? So hot outside? So hot outside. You would have had your lunch. Now you're here in L7. And it so happens that, what should I say? So you had your lunch, it's a hot day outside, you're here in L7, it's all chilled out here, air conditioned out here. In front of you are a bunch of TA 101 slides which I'm going to be, going through. Ideal situation for you to doze off. Isn't it? Isn't it? Is that the reason why you're here? All right. I won't blame you. If I were you, I would probably do the same. So I'll try my level best to keep you awake. All right, so let me get started. This is about 10 minutes past 2 almost. New topic, interpenetration of solids. As I said, we are going to be covering 4 plus 1 lectures more. The 5th lecture is going to be very interesting. All right, already. The 5th lecture, if I get a chance to take it, it's going to be very interesting. It's got nothing to do with engineering drawing, but a lot to do with what you're going to be doing later on in your lives. If I get a chance to take it, that is. Anyhow, so last time I ended up by posing this question to you. So given 3 points, is it possible for us to draw a hyperbola? Is it? Is it? Yes or no? Yes? Who says yes? Given 3 points, is it possible for us to draw a hyperbola that passes through these points? Okay. So if those who say yes want to think a little further, generic equation of a conic, 6 constants. 6 constants. How many conditions you have? 3. You think it's possible? Still? I won't know. Let's see. How do you get a hyperbola? How do you get a hyperbola? You have a cone. Well, so I'm not really sure if I would be needing additional conditions to have a hyperbola pass through these points, but let's investigate further. So if you think about how we get a hyperbola, this is how we do that. So we have a cone, and if we have a vertical plane, need not be vertical. If you have a plane that intersects with the cone, cuts it out, then the intersection between the cone and this plane, the red plane, is going to be a hyperbola, right? So this plane can be vertical, it can be parallel to the axis of the cone, or it could be slant. What could it not be? It shouldn't be passing through the If I have this situation, what do I get? We get a parabola. Otherwise, we get a hyperbola, right? All right. So this situation, so we have a cone, we have a plane that cuts the cone, and imagine that these 3 points, they happen to be a result of this process. Okay, so the first point over here is obviously the intersection between the cone and the plane. To get these 2 points, okay, we draw the base of the cone, we project this intersection point down over here, we measure this distance, and if we rotate this cone by 90 degrees, these 2 points are going to be lying away from the axis of the cone by the same distance on both sides, right? Right? Now, if you have this, so to speak, additional information that you have a cone, you have a plane, and you have 3 points which are a result of the intersection between the cone and the plane in red, it is possible for you to draw or construct a hyperbola. And this is how it could be done. So, construct first a rectangle. The length of the rectangle is the distance between these 2 points. The width of the rectangle is essentially the height that this point lies above the base of the cone. Okay? The right vertical edge, divide that edge into equal number of parts. The bottom right edge of the rectangle, divide that also into the same number of parts of equal length segments. Now, this is what is important. From this point, first you number these points from the top of the rectangle to the bottom of the rectangle, and from the center or the axis of the cone up till the end of the rectangle. Okay? So, the sequence is important. Top to bottom on the vertical side, and left to right or center to right on the horizontal. Okay? And from this point, start drawing line segments that join this point to all these guys. 1, 2, 3, 4, 5, 6, 7. Okay? What do you do about these points? You start from the apex of the cone. So, from the apex of the cone, join this point. Now, the point of intersection between this line and this line would give you a point on the hyperbola. Likewise, the point of intersection between this line and this one here would give you a second point. Intersection between this and this would give you a third point, and so on. Okay? So, once you have the intersection points, the points that lie on a hyperbola, join these points and you get a hyperbola. Okay? All right. Now, this is only possible if these 3 points, they happen to be such that you can extract the information about the cone and the plane that is cutting the cone. Okay? Let me ask you an inverse problem. Of course, this hyperbola is symmetric, so you would see the other side as well. All right. So, do you think the additional information is required in terms of the cone and the plane that is cutting the cone in addition to these 3 points? Do you think that? So, if I give you 3 points and if I give you nothing else, is it still possible for you to draw a hyperbola? Or if I give you these 3 points in such a way that, you know, the information about the cone and the plane that's cutting the cone is available to you, you would be able to draw this hyperbola? Huh?
It might not be unique if you could do the same.
Yeah, this is what my second, so to speak, inverse question is. Now, given these 3 points, is it possible for you to find a unique set of a cone and the cutting plane? In other words, is it possible for you to figure if the information about the cone and this cutting plane is implicit within these 3 points? That's the inverse problem, and think about that. Think about that, because last time a bunch of you guys came to the board, took the mic and started describing different techniques to construct a parabola given these 3 points. So I thought maybe it was possible. Yeah, so think about that. All right. So for today's lecture, I'm going to be using a special pointer. Okay, so this is my teacup. Okay, and this is my pointer. And the point that I'm trying to drive through is interpenetration of solids. This is the first example that we are going to be doing. So imagine that this is a cone, imagine that this is a cylinder, okay, and imagine that you have put the cylinder through a cone, okay. So of course you would have made some cuts, okay, on this side of the cone and on this side of the cone. The problem is very simple. Figure out these cuts, what the shape is, okay. An extension of this is what you're going to be possibly doing in TA 201 when you're working with sheet metal. So a cone is a developable surface, right? Is it? Yes or no? So is cylinder. So you can actually cut the cone out and spread it out on a plane. How's that going to look like? It's going to look like a big sector. Nah? What? It's going to look like a big sector. Likewise, a cylinder, for example, you can cut it out and lay it out on a plane, and it's going to look like a rectangle. So first things first, given the positions of the cone and the cylinder depicted by these 3 views in, it doesn't really matter, first angle or third angle, cone cylinder here, cone cylinder here, cone cylinder here. Figure out the intersection curves, or in a single word, interpenetration between the 2 solids. Okay? A question that you might want to ask yourself: where or which view would you possibly use to figure out where the intersection points would lie? In other words, let me rephrase this question. So which view will tell you the best, or which view will give you the best information about the intersection points between the cone and the cylinder? Would it be the top view, would it be the front view, or would it be the side view? Side view. Wonderful. Okay. Where would the intersection points lie? Huh? Where would the intersection points lie? So you say side view, all right, but where would the intersection points lie? Huh? Would I be correct if I say that the intersection points are going to be lying on this circle? Right? Now the second question is, how do I extract these intersection points? How do I extract these intersection points? I'll have to do something to represent my cone, right? I'll have to do something to represent specifically the slant surface of the cone. Okay? To do that, this is what I would do. I would divide the base of the cone in the top view into equal number of parts. Okay? And this is where things become very, very important. This is where labeling becomes very important. So you need to be very careful when you are labeling, because if you are not, then you will mess things up. I number these points anti-clockwise 1 to 12. Okay? Once again, I divide the base of the cone into, let's say, 12 equal parts. Could be 15, could be 9, could be 10, whatever. They have to be equal. Right? They need not be equal as well. Now, once I do that, I start taking projections of these points on the base of the cone onto the front view. Okay? Be very attentive, be very careful. and then I start labeling the points on the base of the cone. Now, which is this point? Great. How about this point? Wonderful. 2, 6. Great. What? 1, 7. Next. 8, 12. Next. 9, 11. Next. 10. All right. Now, I'll do the same exercise. I'll represent these points over here onto this base of the cone, the profile view, and for that I'm going to be using this 45-degree line. So essentially I'm going to be taking these projections, and transferring them onto the profile view. The reason why I said the numbering is going to be very important is because here you would note that the numbering will change. Of course, so when I do that, I'm going to be joining the apex of this cone to all these points on the base of the cone. Okay? Same thing. Now, what would this point be? Great. 8 and 6. Next. 5 and 9. Next. 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 Last. Great. Now, what you have noticed is two things. One, that's going to be very easy for you to extract the points of intersection from the profile view. The points of intersection are going to be lying on the circle. And once you have these, what I call generators or select lines, they essentially represent what? The slant surface of the cone, right? Your intersection points are going to be the intersection between the slant surface of the cone and the circle. He is a little late, but that's okay. All right, so your intersection points are going to be the intersection between these lines, which represent the slant surface of the cone, and of course the circle. Okay? All right. Your first point of intersection will be here. Okay, what is this point? Intersection between which line on the cone, on the surface of the cone? 4 and 10, yeah, and the circle. Project that onto, call it point A, project that onto the front view. Okay. Now, in the front view, how would this show up? How would this show up in the front view? It would be on what slant lines? 4 and 10. Where is 4? Here. Where is 10? There. So point A is going to be on these two lines in the front view. Right? Right? Okay. So of course, in fact his timing was just perfect. So imagine that this is a cylinder, imagine that this is a cone. Okay? And this is how you are actually seeing the interaction between the cone and the cylinder, like so. Okay? There would be a point of intersection here, and there would be a point of intersection here, right there. So what I would do is I would keep this on the chair in front of you, so that while I am working with the slide, you can imagine how the intersection is going to shape up. Maybe I could have used this table better. All right. Now, the other two intersection points are going to be here and here. Okay? So, point B would lie on the slant line 5, 9. So, go on to the front view. 5 is here. 9 is here, and it is at this height. So you'll have point B here and correspondingly point B there. Okay. Likewise, there would be another intersection point on the other side. Okay. So let me call this point L. L will be at the same height from the base of the cone. Okay. And L is also going to be lying on 311. So 311 is here and here. Okay. So be very careful where the intersection points are going to be lying, because tracking that is very, very important. Okay. Once you understand this, third intersection point on the circle lies on leader 6, 8. Project that, call it C, project that onto the front view. Okay. Identify where leader 6 is or where generator 6 is here, mark that. Where generator 8 is, mark that. Okay. There would be an intersection point on the other side of the cone, call it K, and K would essentially be lying on the same generators here and here in the top view. Okay. Now, this is, so in the third angle projection, this is what the profile view, right? So if you turn it by 90 degrees this way, this part is something that's going to be facing you here. Okay. So this part is something which is going to be facing you. This part is going to be behind you. So understand that. Okay. So these two intersection points, they are facing you, and correspondingly the other two intersection points are behind the cone. Okay. So understand that. Rest is a little mechanical. So DJ, they lie on 6, 8. Project that, identify 6 and 8. Okay. E and I, they would lie on 5 and 9, 3 and 11. 5 and 9 would be here. 3 and 11 would be here. And eventually the last point, G, that will be lying on slant line 4 and slant line 10. Okay. All right. So your intersection profile pretty much is, mic went off. No. Your intersection profile pretty much is done in the front view. Okay. Join these points, and this is how your intersection profile will show up. Okay. All right. So once you have drawn these curves, transfer these points onto the top view. Once again, be very, very careful. These points, they have to lie on specific slant lines on the cone or generator lines on the cone. Okay. For example, this one, where would this lie? 4. Great. This one would lie again on 10. Okay. And these are points A. How about this one? Huh? 3 and 5. Careful. How about this one? One would be on 5, the other one would be on 3. Okay. Likewise, this one would be on 9 and 11. So 9 here, and if you project them upwards, okay. So labeling is important. B would be on 5 and 9 respectively, and L will be on 3 and 11 respectively. Okay. Project this point. Where would that be? Huh? So think about this. So this point, they actually represent 2 points, C and K, right? So this point would lie on 2 and 6. Let's see where it is. 6, all right. And if you go on to the profile view, point C lies on 6, right? And K would lie on 12, right? No, K would lie on 2. Yeah. Okay. Likewise, from the right, these points would lie on leaders or generators 8 and 12 and so on and so forth. Okay. So keep projecting, be very careful. Those intersection points, they have to lie on specific slant lines. Okay. I'll go a little slow so that you can follow. And labeling is very important. So if you mess up the labeling, then you are going to be messing up the entire procedure. So labeling is very important. All right, so looks like you have all the intersection points in the top view. Now, let's look at the profile view now. Now, if you're looking at the top of this assembly of the cone and the cylinder, which points are visible to you? Which of these points are visible to you? The points above the, yeah, so these points, all the points above this axis, this horizontal axis of the cylinder, they're going to be visible. All the points below this axis, they will be invisible, right? So this part will be visible, A, B, C, D, okay, on both sides, and this part will be invisible or hidden. Okay. All right. Now, if you want to figure the rest of the visibility of the cone cylinder, this is how it's going to be. So this part of the cylinder is visible, of course. This part is visible. This part is inside the cone, so it's hidden. Of course, these vertical edges or these vertical circles are visible. Visible, visible. This part is invisible again because it's inside the cone. Okay, and this part of the cone is visible. Okay. Now, notice that I have not shown these edges using hidden lines. Why is that? Why is that? They have to be removed so that the cylinder is accommodated within the cone. Okay. Likewise, the same thing. Top view. This part is visible. This part is visible of the cylinder. This is inside the cone, so therefore it's hidden. Visible, 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 visible. This part is inside the cone again, so it's hidden. This part of the base of the cone is visible. This part is below the cylinder, so hidden, visible, and hidden. Okay. Now, notice what's happening here, and likewise what's happening there. The state of the line is changing, right? So, the cylinder is visible up till this point, and then it's going inside the cone. Okay, and then it's coming out of the cone, and it's visible again. And this is happening where? At the junction, of course, where the cone and the cylinder are interacting, right at this intersection point. Okay, just a double check. So this is called the select line method or generator method. So once again, to summarize, start by looking at the three views carefully. Start by observing the three views carefully. Number one. Number two, figure out which view will give you the best information about the intersection points, most direct information about the intersection points. In this case, it was the profile view. So once you have figured that thing out, okay, in this case, represent the surface of the cone using these generator lines. So they are essentially the slant surface of the cone. They would represent the slant surface of the cone. And of course, the points of intersection would be between this circle in this example and these slant lines. Once you get the points of intersection, label these points very carefully. They have to lie on, certain lines. Okay. Once you label them carefully, transfer them onto the front view and the top view. Straightforward. Okay. The same example using a slightly different method, and that is the method that I am not quite sure if you guys are still comfortable with, the cutting plane method. You guys probably didn't do very well with the quiz with the cutting plane method. All right, so here it goes. I'll go a little quick with this. So the idea is very simple. So you have the assembly. So you have the assembly of the cylinder and the cone. Okay, just slice it using a bunch of parallel planes. Okay, slice it using a bunch of parallel planes. Now, if you slice the cone with a plane parallel to the base of it, what do you get? A circle. And if you slice a cylinder with the same plane, what do you get? A rectangle. So your intersection points will be what? Your intersection points will be essentially the intersection between the corresponding rectangles and the circles. This is what the basic idea is. Okay. Okay. So you have this view, for example. Slice it with a bunch of horizontal planes. The green planes are those cutting planes. Number them 1, 2, 3, 4, 5, 6, 7, 8, 9 from top to bottom. Okay. Now these planes are going to be intersecting the cone at certain heights. Project these guys up. In the top view, the intersection between the plane and the cone will appear as a what? You guys are dozing off. As a what? Great. So each plane will intersect the cone at a circle. Sketch those circles in the top view. Okay, and of course, don't forget to name or number those circles. So from inside to outside, they are numbered as 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now from the profile view, you know that these planes are also cutting the cylinder. Okay, so you would have this intersection point, these two intersection points, and so on and so forth. So this portion over here will essentially be a rectangle. Okay, project this rectangle onto the top view for each and every plane, each and every cutting plane. Okay. All right. Okay, so this point here will essentially be a line, a rectangle with no area. This would be rectangle BB, rectangle CC, rectangle DD, and finally rectangle EE. Okay, and remember that the same rectangles will be below the axis as well. Okay, so once you have identified or named those rectangles, name them in the top view. So A would be a line, BB would be this one, CC would be this one, DD would be this one, and EE would be essentially the rectangle corresponding to this plane here. Okay, now your first point of intersection is going to be between some circle and some rectangle. Can you give me that circle? 1 and rectangle A, first point. Second point is between 2 and BB. How many points do you expect? 2. One at the bottom, the other one at the top. Third one is between circle C and rectangle CC, or circle 3 and rectangle CC. Okay. One at the bottom, the other one at the top. Fourth one is in between 4 and DD. Okay. Bottom and top, and fifth one is of course in between circle number 5, which is here passing through the axis of the cylinder, and this rectangle here. Okay. And don't stop here, keep going down. Okay. So this one is in between, let's say DD or maybe CC, right? Rectangle CC and circle what? Circle what? 6. Okay. Next one, BB and 7. Is it BB and 7? No, it was C and 7. Okay. This guy here and this guy here, C and 7. So BB and 8. Okay. And of course eventually a single point here, A and plane number 9. Okay. This guy is symmetric. Once again, it's going to be these intersection points above the axis, they are going to be visible. The intersection points below, they will be hidden, they will be invisible. Okay, so this is solid and this part is hidden. Okay, so the intersection is symmetric, mirror image. All right, and drop the corresponding intersection points down onto the front view. Where would you want to drop this? To which plane? Which plane? So here you have plane information here. So which plane? Plane number what? Plane number 9. These two guys here. Which plane? Where do they lie? Where do these points lie? On which plane do they lie? What? Plane number 8. Great. These guys, plane number 7, plane number 6. Keep working backwards. Eventually up to plane number 1, and of course you have this intersection point. Well, this intersection is again symmetric, so get the mirror image, get this intersection point or intersection curve. Right? So do you expect the two methods to give you the same result? Do you expect the two methods to give you the same result? Compare. Now you have done AutoCAD. If you do 3D modeling in AutoCAD, take the cone of the same size, take the cylinder of the same size, perform intersection, okay, get the cylinder into the cone, perform intersection, and if you try to compare that with what we have, they are identical. Yeah? All right, so why is this exercise important? Why is this exercise important? take a look at this example. Okay. Now, what I had done is I had made a little modification to this cone. I have cut a certain feature of this cone. I have cut a certain feature away, and this feature is such that it allows this hexagon of the prism to go very nicely into this cone. Okay, with barely any effort. I'm making some effort. Okay. All right. So if you do not know how to do this, or if you cannot do this, this is not possible for you. All right. So this method permits you to figure out the intersection between the hexagon of the prism and the cone, okay, and eventually figure out the part that needs to be cut away from the cone, so that when you fold it up, it's a lot easier for you to let this hexagon of the prism pass through this cone. Okay, something that you'll be possibly doing in TA 201. And of course, this is the portion which is cut away from the cone. All right, another example. So this time we have a rectangular prism. Okay, rectangular prism passing through the cone. Once again, question number 1: which view will give you the right information about the intersection points? Profile view. Where would the intersection points lie? Where would the intersection points lie? They will lie on this edges, or these edges. Yeah. So essentially the problem is to figure out the intersection between the slant edges of the cone, slant edges that lie on the surface of the cone, and these edges, right? Same thing as in case of example number 1, previous example. All right, so this is your first intersection point. It lies on this horizontal surface. I'm going to go a little fast. All right, so just follow this. Okay. All right, so there are 2 intersection points over here. The second intersection point comes from here, the interaction between the generator 5,9 and this edge. Okay, correspondingly there will be 2 intersection points on the front view. Okay, BC. The third one comes from here, lies on 6 and 8. Okay, fourth one would come from here, possibly. Yeah. That would lie on number 7 and 1. 7 and 1 would be at the center. Here. Right? So keep following this procedure. So H and I would lie on 6, 8 and 2, 12. J and K would lie on 5, 9, 3, 11. And eventually the bottom intersection point would lie on 4 and 10. What? All right, so if you think about this face of the prism, okay? If you think about this face of the prism, well, of course, there would be another intersection point that comes from here and here. Okay. Visibility. All right. So a part of it is outside, a part of the pyramid is outside the cone. Some part is inside, so some part is hidden. All right. This part is visible. This part of the cone is visible. And of course, this edge is visible. Now, if you think about this plane, what would this plane give you? So this plane on the prism, what would this plane give you? Would give you ellipse. Yeah? What would this plane give you? It will give you a parabola. So, the top part is the elliptical part, okay, and the bottom part is the parabolic part. Yeah? This plane should be parallel to the what? So, what you're saying is this plane should be actually here somewhere? Oh, this will give you an ellipse. So, both are ellipses. Are you sure? What? It's a half ellipse, all right. So you guys are not sleeping after all. Good. So this is okay. So all right. So project these guys up onto the respective slant lines on the cone. Be very careful with regard to where these intersection points are going to be. Okay, you can figure this thing out. This is not very difficult. You can figure this thing out where the intersection points are going to be. Now, which part will be visible in the top view? Which part of the curve will be hidden in the top view? Which part of the intersection curve will be visible? Which part will be hidden? Would this part be visible? Would this part be visible? No. So everything from here up will be visible, everything from here down will be hidden. Okay, so this part of the prism is visible, that is hidden, this is visible, 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 visible. That part of the base of the cone is hidden, part of the base of the cone is hidden, visible, visible. So the center part is going to be visible because and the bottom part or the other part will be hidden. So the part corresponding to this region over here, that will be hidden. Okay. Once again, if you go back and if you work it out on AutoCAD, this is what you would see. All right. Coming back, you know, I mess up my coordinate geometry. So a plane that is parallel to the base of the cone, if it cuts the cone, it will give you a circle. A slant plane will give you an ellipse, right? How do you get a parabola? One at a time. If it is all right, so if it is parallel to the slant line, anywhere you will get a parabola. All right, here you will get a hyperbola. This one will give you a hyperbola, right? So it need not be vertical. So a plane need not be parallel to the axis of the cone to give you a hyperbola. So it could as well be like so, till it is again parallel to the slant line. That is when you will get a parabola. And of course, this will give you a what? This will give you an ellipse. All right. So fix this.